and Greenewald is from the Chinese Academy of Science, and he's going to talk on compatibility.
Quartet compatibility, yes. Maybe one quick word why I'm from the Chinese Academy of Sciences. Actually, there is a partner institute funded by the Max Planck Society from Germany and the Chinese Academy of Sciences. And since the Germans gave quite some money for that institute, they also sent some researchers working there. So I'm talking about quartet compatibility today. When I told David Bryant once that I'm working on some problems in that field, he said, what's left? So it's not a very modern field. Most results are quite old, and I think most biologists are disappointed about quartet methods. So there has not been too much work in the recent past. I have done something anyway. So the motivation of this is, given a set of phylogenetic trees with overlapping taxa sets, so not necessarily quartets, you start with a few phylogenetic trees, and you want to build one big supertree. So this is a compatibility problem, or you could also just say the supertree problem. This is a popular problem, and new methods are developed all the time. I need a few formal definition. I will keep it short and very simple because most of you will probably be familiar with that. It's basically the notation that you find in Mike Steele's and Charles Sample's book. So we want to go from small trees to big trees, which turns out to be very difficult. The other way around is very simple. If you have a big tree and you want to find the tree that for a subset of the taxa set that is induced by the big tree, you consider the restriction. So you just remove the taxa that you're not interested in, and then you suppress degree 2 vertices to make sure that you get a phylogenetic tree again. So that's very easy. Next term we need is displaying. A big tree displays a small tree if the small tree is the restriction of it, which of course implies that the taxa set of the small tree is included in the taxa set of the big tree. So I have two examples. Here you see some red edges of the big tree. So that is a tree induced by the taxa H, A, D, and C here. So you can see that the small tree on the right side is displayed by the big one on the left side. One example where that is not the case is here. You see the red edges, they have a degree 4 vertex here. So that is not a binary tree, so that is not, the right one is not the restriction of the left one to the small taxa set. So finally, I have to say what a quartet is. Of course, that is just a binary tree on exactly 4 taxa. So if we fix 4 taxa, then there are 3 possible quartets. And usually we write A, B versus C, D with this vertical line to talk about such a quartet. Why are quartets of interest? They are basically the smallest bit of information for unrooted phylogenetic trees. So if you have only 3 taxa, then there is only 1 tree topology and you have no information. And if you have 4 taxa, then you get, it's the first case where you have different situations. So, of course, the main question is, if we have a set of quartets, can we find one tree that displays all the quartets? In that case, we say the quartet set is compatible. And of course, mathematicians are interested in existence. And if you have existence, then you're interested in uniqueness. So in this case, if there is exactly 1 tree that displays all the quartets, or this doesn't have to be quartets, it could be other smaller trees. So if there is exactly 1 tree that displays them all, then we say that the collection of smaller trees defines the big tree. What is known about compatibility? So this is more a complexity slide. So there is this result from 1992 that it's NP complete to decide whether a given set of quartets is compatible or not. So at this point, you can already give up the idea, just take all the quartets you can find and build the big tree that displays them all. So this will usually not work. On the other hand, it can be decided in polynomial time whether a set of quartets with cardinality exactly the number of taxa minus 3 defines a phylogenetic tree or not. And I will say something more about this result later. And finally, given a set of quartets and a tree that displays Q, and the question is that the only one? And this complexity of deciding this question is still unknown, and it is the only open question in the phylogenetics book by Mike Steele and Charles Semple. Actually, I have some idea how to prove that is NP complete, but that is under development, so I have to state it here as an open question. Next definition now that I need to present my own result. So I call a set of quartets thin if every subset of k taxa for k larger equal 4 contains at most k minus 3 quartets. So that means if k equals 4, for 4 taxa we have at most 1 quartet. Of course, if we would have 2, we would have a conflict, and that could not be compatible. And so for 5, we are allowed to have 2 quartets. For 6, we are allowed to have 3 quartets, and so on. And the result that I proved is that if a quartet set is thin, then it is compatible. So that is a very easy statement. The proof is not quite so easy. It is maybe three or 4 pages long. And this is somehow an interesting result about quartet compatibility, but the main reason why I think it is interesting, or the reason why I found it, is because I was looking for an alternative proof of this theorem by Steele from 1999, which has every minimum defining quartet sets contains a maximal hierarchy of accessory subsets. I don't really want to go into the terminology. A minimum defining quartet set means you have number of taxa minus 3 quartets. It's easy to see that you need at least so many quartets to define a phylogenetic tree. And the proof of this theorem, or their proof, is really hard to read and really long. And the full proof has only been published in Sebastian Böcker's PhD thesis. And Julian and Steele said in a more recent paper, this is one of the most mysterious and apparently difficult results in phylogeny. And so I had the idea to get rid of this mystery a little and to try to find an alternative proof. And I can just tell you here that applying the theorem 1 that I presented a minute ago enables me to come up with an alternative proof of this theorem, which is then only 7 pages long. So, and I think it's understandable. I had an intern student who understood it within 1 week. I want to quickly explain the result. So, maximal hierarchy of accessory subsets. So what happens, we start with the collection of quartets, and then we find that there is a pair of them which defines 1 tree on 5 taxa. And then this may happen for another tree. And then you will see that these 2 5 taxa trees define 1 bigger trees on how many taxa we do have? 7 taxa in this case. So this is a hierarchy. It's a tree of trees. This is a rooted tree then. But every tree is defined by its 2 children. And the theorem says that you can always find this situation for minimum defining quartet sets. And that's also the reason why it's NP complete to decide whether such a set of quartets is defining or not, because you can just do these pairwise comparisons. A question in this complex, or a question that is somehow that you might have in this context is what about freely compatible quadruple sets? You saw in my theorem that I didn't really need any information about which quartets are chosen. I just needed information about for which quadruple we have 1 quartet in our set. So I can just do that for quadruples. I take a set of quadruples, say it's freely compatible if we have at most k minus, no, if we can choose whichever quartet we want for every quadruple, and it's always compatible. And we can say a set of quadruples is thin if for every subset of taxa with k elements, we have at most k minus 3 quadruples. So that's just corresponding to the theorem. So the theorem says that every thin set of quadruples is freely compatible. And at that point, Mike Steele asked the question, is that it's a converse true as well? Is every freely compatible set of quadruples thin? And the answer is no, it's not. A student of mine, Lee Junrui, found this example. You take 13 quadruples on 13 taxa, such that each two of them overlap in exactly 2. So that is a block design. And then you can choose whichever quartets you want, and it will always be compatible. So we just checked that by computer. Now I will come to some other way to visualize quartet sets. So what is a quartet set mathematically? It's a pair of pairs. If you want to visualize pairs of a set, or then you would usually draw a graph, because a pair is just an edge. So in this case, we always have pairs of edges, and what we do there is we just draw 2 edges and color them with some color corresponding to the quartet. So this is a good way to draw a quartet set, and it turns out it is also kind of useful. So we introduced this concept in a paper with Peter Humphreys and Charles Semple that we have submitted, and we will resubmit a new version 6 weeks, hopefully. So, and why is this useful? We can get the traditional interpretation how to produce a phylogenetic tree by pairwise grouping. So we start with this given quartet graph, and then we do some operation. We always choose 2 adjacent vertices and identify them. Like here, we could choose A and B. And then we do this agglomeration operation as it is done by neighbor joining and similar programs. So what I did there is I identified the 2 vertices A, B, and I removed the other edge of the same color. And in here, I went from the bush to the tree that separates A, B from the rest of the taxa. So now we could do the same thing again and group F and E together. So now we have only 2 edges left and 1 quartet. We do it once more. We get this phylogenetic tree displaying the 3 quartets. An interesting thing here is you see immediately from the graph at the beginning that by symmetry, you can also group the cherries slightly different. So this is a useful way to draw quartets and also to see how you can find a tree. At least it helps you a little. Of course, you can't beat the NP completeness. What you can use a lot in quartet compatibility is closure rules. So here we have an inference rule. A quartet set is A, B, C, D, and B, C, D, E, visualized by this small graph there. And they define the tree on 5 taxa. So all the other quartets displayed by that tree are inferred by these 2 quartets. So that is one closure rule. There are quite many closure rules. So one approach is you just apply all closure rules, and then you might see whether it's compatible or not. That's not a contradiction to the NP completeness, because there are infinitely many closure rules. So that would not really help for an algorithm. But this example shows that closure rules will not in general help at all, because it is strongly closed but not compatible. Strongly closed means whenever we remove one quartet, the thing is compatible, but it does not infer any other quartets than the ones we have in the set. So here closure rules will not help to find out that the quartet set is incompatible. So this is, you just take the graph, it's just a cube, and you group together the opposite edges. Finally, I have constructed an incompatible quartet set with little overlap. So in 1992, Mike Steele used a counting argument to show that there are incompatible sets such that 2 quartets in the set have at most one taxon in common. Intuitively, you would say such a set should be compatible. You just glue them together. But after doing that a few times, then you have more overlap, and then it doesn't work anymore. So this was in 1992. So it's clear that such sets must exist, but none of them have really been constructed. And so we used some educated guess together with computer power to finally construct such a set. So here we have 15 points. I visualized 3 quartets. There is the 15 points can be grouped into 3 5 circles, 1 interior circle, 1 middle circle, 1 outer circle. And then there are 3 kinds of quartets here. For example, you see on the outer circle there is this edge going from one vertex to the next one. And then corresponding, you go from this vertex 2 vertices further in the interior cycle. So there are these 3 kinds of quartets. And then you just rotate that by 72 degrees. And then you get this a little complicated looking graph. It's not really symmetrically drawn. Otherwise, it could be done nicer. So this is 15 quartets on 15 taxa, and they have the property that Mike described in his old paper. That's it. Cheers.